When we look at a cloud of multivariate data, we may perceive groups based on density or proximity. But these boundaries are subjective until we apply objective criteria to describe them. Since we generated this dataset, we can reveal the structure. To characterize these groups in real-world data, we use specific mathematical frameworks. We will compare three approaches: K-means, fuzzy clustering, and expectation-maximization, and we'll show they are made using the same algorithmic frame. As an extra, we'll show how robustification can be inscribed in this same framework, and why EM is not necessarily made for Gaussian distributions. We begin with the simplest clustering algorithm, K-means. Each row represents one of our data points, defined by its x and y coordinates. To start the iteration, we choose two random centroids in the space. On the right, we have our distance machine, ready to calculate the proximity of every point to both centers. Each point can now be assigned to the cluster represented by the closest of the centroids, identified by the smallest distance. Let us put a 1 instead of the closest distance and a 0 instead of the remote. We color the data points based on these assignments and retract the initial artificial centroids. K-means will now update the centroids by calculating the mean of the points in each cluster, with 11 red points and 9 blue points. Each red point is assigned a weight of 1 over 11, and each blue point 1 over 9. By averaging these coordinates, we find the new centers of our clusters. We update our centroids to these new positions, clearing our workspace for the next iteration. K-means is an iteration. We repeat the procedure. In this second pass, the machine recalculates distances to the new centers. Let us put a 1 instead of the closest distance and a 0 instead of the remote. We color the data points based on these new assignments and update the centroids to their new positions. If we repeat the procedure again, no point will move from one cluster to the other. In that case, we are done. The result is a partitioning of our 20 data points. We now also have the centroids, so that for any new point, we can instantly classify it based on its distance to these centers. Fuzzy C-means an analysis of soft clustering. Unlike the discrete partitions of K-means, fuzzy clustering provides a continuous membership framework. This approach replaces binary assignments with membership grades. A single point may possess partial belonging to multiple clusters simultaneously. Proposed by Zada in 1965, the theory of fuzziness was central to the high expectations and subsequent hype of the 1980s AI research wave. The fuzzifier M determines the degree of cluster overlap. As M increases, the aim for absolute precision gives way to blurred boundaries. Row normalization is maintained through this membership objective function. In K-means, normalization meant that exactly one value is 1. In this more general system, the sum of belonging for any point must equal 1 across all clusters. Centroid positions are recalculated as a weighted mean. This process is similar to K-means, but incorporates the weighted influence of every point based on its membership grade. As we will now see, despite these mathematical refinements, the underlying algorithmic framework remains almost unchanged. We apply fuzzy C-means to our dataset of 25 points, maintaining the same framework as before. We choose the fuzzifier M equals 2. This governs the degree of overlap. As in K-means, we begin by establishing two initial centroids in the data space. The distance machine first calculates the standard Euclidean proximity for every point. Now the logic diverges. The machine applies the fuzzy normalization formula, converting distances into soft membership grades. The points are colored by blending. centrally located points become purple, indicating shared membership. Centroid positions are recalculated as a fuzzy weighted average. Notice the values in the header updating. The process repeats. Row after row, the machine recalculates the grades against the refined centers, and the diagram adapts. The iteration stops when the change in centroid positions falls below a threshold, epsilon. The final result is a fuzzy membership table and stabilized centroids, allowing any new point to be classified based on its distance to these centers. Until now, we've treated clusters without assuming a model. But real-world data may be generated by distributions. In this example, we assume our data was born from two distinct bell curves. The expectation-maximization algorithm assumes what we see here is the evidence left behind by these hidden bell curves. Here, each bell curve is defined by its position, width, and weight. These weights tell us the proportion of the population belonging to each distribution. But notice, EM is a universal engine. Its job is to untangle any composite system back into its original components. The Gaussian bell curve is not the only distribution family, even if it is associated with most explanations of EM. Let's go for a Poisson mixture first. Consider a policy to ensure medical treatments in sports clinics. We may expect one Poisson distribution of claims, but the reality turned out otherwise. Let us investigate the possibility of two distinct groups of policyholders: amateurs who claim less frequently, and professionals who use the insurance more often. Let's use the EM algorithm to separate the clusters, find the proportions and the distinct lambdas for each cluster. We take our example into the table, similar to the k-means and fuzzy examples. We initialize the lambdas and pi proportions for our two clusters in the header. Iteration 1, the machine calculates the initial likelihoods. In the expectation step, we apply row-wise normalization, converting raw likelihoods into posterior responsibilities. To update our parameters, we calculate the weighted average of the claims for the new lambdas and the average responsibility for the pi proportions. The parameters hop as the model begins its alignment with the data stacks. Iteration 2. The machine calculates the likelihoods again based on our improved estimates. The parameters adjust further, handling the cluster overlap with greater precision. Iteration 3. Another pass to approach the optimal fit. The shifts are now tiny as the model stabilizes. Iteration 4. We refine the model one more time as we approach the ceiling of the likelihood surface. The parameters are now nearly stationary, signaling that we have reached a stable fit. We stop when the parameter changes fall below epsilon and the likelihood is maximized. The table served its purpose, but the real value lies in these parameters that now describe the entire population. Let us now apply the EM algorithm to the 2D cluster, which we believe comes from a mixture of two isotropic Gaussians. We initialize with a stochastic guess. We do not display the table anymore, but it is still active in the background, where the weights are calculated by normalizing the likelihoods for every point. In the first iteration, the means are updated as the weighted average of point positions. The mixing proportions PA are updated as the average responsibility. By the second iteration, the variances, sigma, are recalculated using weighted squared distances. We monitor the shift in these parameters against our epsilon criterion. The algorithm stops once the change in parameters falls below epsilon, signaling that the model has sufficiently stabilized. Standard clustering assumes data is well behaved, but extreme outliers can pull our means away from their true centers. To robustify, we adjust our computations. In k-means, we move to k-medians, calculating the center as a component-wise median. Because the median only cares about rank, extreme values cannot shift the centroid. For fuzzy C-means, we increase the fuzzifier to dilute the influence of distant points on the weighted centers. In the EM algorithm, we swap the usual distributions for heavy-tailed ones. We replace the Poisson with a negative binomial to handle over-dispersion, and the Gaussian with a student's t-distribution. This ensures the peak of our distribution remains stable even when the data has long, noisy tails. In the Gaussian case, we can go further and replace isotropic, round Gaussians with elliptic ones, allowing different variances along each axis. We avoided this earlier to keep attention away from covariance matrix technicalities.